This video is about tangents, velocities, and rates of change. We're in the context of calculus topics. We've already discussed the necessary topic of a limit, as we'll be using eventually in this process. First of all, for our notes, let's go ahead and recall just some basic algebra that we're going to need here. First of all, there's a slope formula, often written as m equals, and then y2 minus y1 over x2 minus x1. That's just a famous formula in algebra class for a slope of a line. Of course, the values involved in this formula are the points x1 comma y1 and then x2 comma y2. So those 2 points, x1, y1 and x2, y2, are on a line, and if you know the points, you can plug those values into this formula to generate the slope of the line. Of course, slope is rise over run. That goes way back to some beginning algebra topics. Now, in this consideration, what we want to do is understand what a tangent line is. If we consider a curve, some function curve showing up in a quadrant 1 graph here, and then somewhere on the x-axis, let's just mark a spot and call it A, where the x-axis equals A. Then on this curve, directly above A, we'll have a point, and of course that point is A comma f of A, where the function is f of x. You could say y equals f of x. So a comma f of a is a point that we have on our curve. Now a tangent line is a line that intersects a curve at exactly one place, or one point you could say. So I'm just going to roughly sketch one. It'd be a line that intersects our curve only at this one place, and I'm of course picking on the place a comma f of a. That's the tangent line to this curve by definition. Now, a consideration could be then, okay, if this is a line, any line has a slope, unless it's a vertical line, then it's undefined. But a line has a slope, and as we just recalled, there's a formula for the slope. It's this y2 minus y1 over x2 minus x1. Well, okay, the problem comes then, how can I find the slope of this tangent line if all I have is a single point? The slope formula requires 2 points, as we just discussed. One way that mathematicians tried to resolve this problem would be to add another point to this curve. So let's move further down the x-axis to the right of A and mark some place, and then directly above that place, let's put a solid point on the curve. Now, what do we call that point? It's a fair question. Well, there are a couple different ways to write this out, but one of the most common and I think easiest ways to understand it is that place further down from A is, in the way we've drawn this, higher than A. So we're going to call it A plus H, where H is some non-zero value that when you add it to A, you move down the x-axis to the right, further apart, or apart from where A was, and now you get another place. In other words, this point directly above this A plus H place would have the coordinates A plus H, comma F of A plus H, just like we defined that in the first point, but now with a different x coordinate in this case. If you connect those 2 points we have now, you get what I've now drawn in an orange line. And of course, since those points are different and the second one we drew is further down the x-axis, when I connect those 2 points, the line I get from connecting them doesn't match the estimation I drew in red of the tangent line. In fact, this second line now that's not the same as the tangent one is actually called the secant line. Okay, so a secant line intersects a curve at 2 places. A tangent line intersects it at 1 place. And you can see how these are both showing up in the same picture, but clearly they're not the same line. So the question becomes, well, how could I make the secant line look more like the tangent line? Well, one way I could do that would be taking the second place I picked on the x-axis, the a plus h place, and moving it closer toward the original a values. So if I were to slide my second place down and mark it closer to where a was, then, of course, directly above that, I would have the point a plus h, comma, f of a plus h, and that point that I had originally plotted there would kind of slide down the curve as the x-coordinate of it slides to the left. The secant line that I would draw in that second place or condition would be actually a lot closer to the original estimate I had for the tangent line in red. So as you can probably tell, if this were a motion picture, if we continued to drag the a plus h value closer and closer in toward a, the point that we plot on the function would be getting closer and closer to the a comma f of a point. And therefore, when we connect the 2 points, the estimate, the secant line, is going to get closer and closer to being this actual tangent line. So here's where things get a little interesting. You may say, well, okay, if the definition of a tangent line is one that intersects the curve at one point, then we're not quite there. I mean, we're getting closer, but we're still using two different points, the a comma f of a and the a plus h comma f of a plus h. And in doing so, we're not really using only one point, so I don't still have the slope right at this a comma f of a place. That's true, but there's a way to fix it. If we consider how we could describe the slope of the secant line, remember the secant line is the orange one, it intersects two places on the curve. Of course, we've drawn a couple of them because we're kind of moving where the second point is. And as we move the point, of course, the secant line would move with it. But the slope of the secant line, using the same slope formula we started with for algebra, the y2 minus y1 over x2 minus x1, that slope would be y2, which you could say is f of a plus h, minus y1, which is f of a, all over x2, which is a plus h, minus x1, which is a. So really, this slope formula for the secant line is the same thing as the slope formula for any old line we learned in algebra class. Same thing. Of course, we're using function notation here, but it really is the same formula. Of course, we can simplify this one step in the denominator. Let's rewrite this as f of a plus h minus f of a all over. If I had a plus h minus a in the denominator, those a's would cancel, giving me just an h down there. So that's the slope of the secant line. But remember, our original goal was to try to find the slope of this tangent line in red. So here's where we can use our friend the limit to help out. So let's now restart and find the slope of the tangent by saying, as we were discussing a second ago, as we move a plus h closer and closer to a, then these second points plotted on our curve are going to get closer and closer together. Now, if they're the exact same point, we only have one point and we can't use the slope formula, which requires 2 points, as we've already written a couple times. So we have to keep them separately as 2 points, but we want a way to bring them as close as possible. Thankfully, we actually have a way to do it. And notice the way that our x values are marked in these 2 points. The first one is a, the second one is a plus h. We can actually bring them closer by simply making h smaller and smaller, right? I mean, isn't a plus 0 really just a? Okay, well, if h was 0, then I would have only 1 point, and then the formula would break down because I have to use 2 points to get the slope. So we can't let h be actually 0, but we have a way to do this, which is called a limit. So we're going to say that the slope of the tangent is the limit as h approaches 0. Okay, remember h approaching 0 would be us walking down closer to the first point from the second. But remember, with a limit, this is why those definitions matter so much, you can approach a value without actually ever getting there, which means it doesn't ruin this formula and take away the fact that we have 2 points. So we'll say our slope of the tangent, m, is the limit as h approaches 0 of f of a plus h minus f of a all over h. That's exactly what we had said about the slope of the secant line. But now with this limit involved, we can call this the slope of the tangent line because we're getting these points so close together that they're essentially one point, which is what the whole idea was, right? A tangent is defined by intersecting a curve at only one point. So the slope of the tangent line is really the limit as h approaches 0 of the slope of the secant line, where h is the only thing separating those 2 points being a secant, 1 point being a tangent. Let's box up this definition. It's going to be very important even going forward. Now, I will say too, this is not the only way to write the formula for the slope of a tangent line. There's one other method often listed in textbooks, and it's just as good. It's no different other than instead of separating the 2 points as a and a plus h, they would separate them with 2 different letters altogether. Ultimately, it's the same thing, and this is probably the most common form of the slope of the tangent line, so I'm going to stick with this one for now. Let's now consider velocities, which really are a general application of what we just saw about the slopes of tangent lines, as we'll see shortly here. Now, this is about velocities, but it can represent rates of change in general. There are other rates of change out there that aren't necessarily speed and direction, which is a common application for velocity. So there are some financial applications and biological applications that still involve rates, but not in a velocity exact kind of way. But nonetheless, this will carry on to other applications as well. Let's consider an axis again and put a place on it. We'll put an a value on the axis, but this time we're going to suppose that s equals f of t represents the position of an object moving along a straight line. So in other words, we're going to label this as the t-axis instead of the x-axis. And we're going to put some curve going through our quadrant here. This curve will represent f of t, our position function s. And so this function, kind of like we just saw in the previous picture, could be analyzed in the same way, where if I say above a, I'll put a point on the function, and that will be the place a comma f of a. Look familiar? Yeah, we just saw that in the picture previously. And then in this application, if I move further down and call it a plus h like we just did before, then of course directly above that we'll have the point a plus h comma f of a plus h. So really this is the same kind of picture we just saw when analyzing the slope of a tangent line. But at this point we're discussing the context of velocity. Now there's a definition we'll consider here, which is what's called average velocity, or sometimes it's called average rate of change, same kind of thing. And it's often defined as displacement divided by time. Well, again, this is a velocity kind of application. Time is really our x-axis. So what happens is often, you can connect these 2 points that we've plotted here on our position function with a straight line. Yes, that's called the secant line, like we just discussed in the previous example. But in this case, you could say average velocity is displacement over time, which is, well, as we've defined already, that would be like the slope of the secant line. So average velocity would be the slope of this displacement line, or this position line, you could say. That would be, as we've labeled it here, f of a plus h minus f of a all over a plus h minus a, which like we already saw turns out to be just h. So again, that's the slope of the secant line, which we're seeing here. That's what's known as just average velocity. So then a fair question could be, okay, if that's the average velocity, or you could think of velocity as a speed, if that's the average speed of something over a certain time interval from a to a plus h, what about the instantaneous speed at one of those values? Like, what is the actual rate of change or velocity right at A? You could probably try to estimate a tangent line to it there at a single point, but what is the actual slope of that tangent line? Well, that's exactly what we were just discussing previously. So now we can say the instantaneous velocity, the velocity at a single point. Okay, so the velocity of an object with position function f of t at time t equals a, that's at only one place, is v of a, the velocity at a, which is given as the limit as h approaches 0 of, a little typo in here, this should be f of a plus h minus f of a all over h. Okay, let me say that again. The instantaneous velocity at time t equals a is given by the following function. V of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h, provided the limit exists. Okay, and this limit is exactly what we just saw in two ways. First of all, immediately here above, we defined the slope of the secant line as this ratio, f of a plus h minus f of a all over h. That's just using, remember, that's just using y2 minus y1 over x2 minus x1. That's the slope formula. Okay, that's all that is. But then even previously, we saw in the case of understanding the slope of a tangent line, that if you add the limit where h is approaching 0, then you're kind of shrinking these 2 points down to 1. And in the application of velocity, if you're down to a single point, that would give you the slope of the tangent line right at that value a, which is what we could call the instantaneous velocity of this object.